Okay, this is going to be the review session for exam 6, and this will be the last exam. Here we are going to cover part of chapter 13. Primarily we'll cover solubility and colligative properties. So there will be questions from solubility as well as colligative properties. Now let's first focus on solubility. In chemistry, we use the term like dissolves like. That means if I have a polar solvent, it's going to dissolve polar molecules or polar solutes. If I have a nonpolar solvent, it's going to only dissolve nonpolar compounds or molecules. Let's go over an example from the book. Chapter 13, I picked this problem, which is number 33. The question is, between CCl4 and calcium chloride, which one is going to be more soluble in hexane? Which one is more soluble in? Now we need to know what hexane is. Hexane, hexa, that's 6 carbon. So let me draw this in the simplest form. 1, 2, 3, 4, 5, 6. That's hexane, carbon, and then the rest would be hydrogen, so that each carbon has 4 bonds. So let's write down that. Now keep this in mind that each carbon has sp3 hybridization. You have 4 pairs of electrons. So this is a tetrahedral structure around each carbon. Each carbon-hydrogen bond has a very small polarity. Besides, they have symmetrical geometry to like a tetrahedral structure. So altogether you can say that this is nonpolar. So all alkanes are nonpolar molecules. So when the question is whether CClO4 or calcium chloride will be more soluble, we have to know more about these solutes. What kind of solute CCl4 is? Cl, 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 Cl. I wrote down tetrahedral. Why? Because there are 4 pairs of electrons, carbon with 4 bonds. 4 pairs of electrons, sp3 hybridization, 109.5. So it will look like this. But the only thing is, all these are made up of Cl. So their forces are going to cancel out. So this is going to be nonpolar. So keep in mind, for symmetrical geometry, when you have all these forces add up, then they're going to cancel out. So this is the nonpolar molecule. Calcium chloride is an ionic compound. How do I know that? Calcium is from far left of periodic table, and Cl is from far right. So there's a big electronegativity difference, and that gives ionic bond. Ionic bond means calcium would be 2 plus, Cl would be minus, like that. So when I say like dissolves like, nonpolar CCl4 would be more soluble in nonpolar hexane. So this is going to be more soluble. So there will be a question like this in the exam where you need to analyze which one will be more soluble in a particular solvent. Similarly, if you look at next problem, 33b, this is 33a. 33b, this is a similar problem, just I'm trying to give you the understanding of it. 33b has benzene. So these 2 solutes, one is benzene. So that's benzene. And benzene has hydrogen for each carbon. Each corner is a carbon. If nothing else is written, that means it's understood it's carbon. So that's benzene. And the other one is glycerol. Glycerol has this structure, CH2OH. Then you have CH OH, then you'd have CH2OH. Obviously, you can see that benzene has all carbon-hydrogen bond and carbon-carbon bond, so this is nonpolar. On the other hand, here you can see that OH bond, these are polar bonds because of electronegativity difference, plus it can give hydrogen bonding. So this is polar as well as H bonding molecule. So remember, like dissolves like. This is nonpolar, so, and that's also nonpolar. So nonpolar, benzene is going to be more soluble. So answer is this is more soluble. The next problem would be number 34 from the book. Here we'll be looking at water as a solvent. Okay, I'm going to pick 34B. Again, that's from chapter 13. It's one of the assigned problems. CH3, CH2, CO, OH. It's an organic acid. And the next one is CH3, CH2, CO, O minus. The question is, which of these two, this is an ionic compound, they gave you sodium. Now why do I know that this is, how do I know this is ionic? Sodium is from far left of periodic table, and this is from far right. So there is a huge electronegativity difference, and so you'd expect ionic bond between oxygen and sodium. So I wrote down like this, and this is a polar and hydrogen bonding. So this is polar H bonding. So you'd also expect this to be soluble, but this is more soluble. This is ionic. So ionic could be, you can see that there's a bigger polarity difference in ionic compound. So this would be more soluble in water. Okay, because water is a polar molecule plus H bonding. And this has a greater polarity, and that's why this is more soluble in water. So keep this in mind. Now if I make a slight change in my question, and let's see whether we can find its answer. This is the question I'm going to make up. Say I have a long carbon chain, 1, 2, 3, 4, 5, 6. And these are all carbon and hydrogen. So I have hydrogens. I didn't write down the 3 hydrogens, 2 hydrogens, 2 hydrogens, so that each carbon gets 4 bonds. And the other one is CCCO, OH. Now the question is, which of these two would be more soluble in water? Both have COOH, both have same kind of polarity. Here you have to look at something else. The something else is this part. This part is insoluble in water, or tend to be insoluble in water. Insoluble part, and this one is the soluble part. In first molecule, insoluble part is pretty big compared to this. So that means this would be less soluble in water than this. So smaller molecule would be more soluble, because this is the alkane end, which is non-soluble part, and here's the smaller non-soluble part and bigger soluble part. So this will be more soluble than this. So make sure you're ready for both types of questions. The next type of problem would be definitions, and that we need to know and understand the temperature effect. So there will be question on definition of molarity, mole, mass percent. Let's make it molality now. I want to remind you these definitions: mass percent, mole fraction, and molarity. Let's first write down the definitions. Molality: moles solute. Solute could be sugar you are adding in water per kilogram of solvent. Kilogram of solvent, that's molality. Mass percent, mass of solute. So at the gram of sugar, for example, total mass of sugar plus water, mass, times 100. So that gives me mass percent. Now the mole fraction, that's the number of moles of solute divided by total number of moles. Total moles of solute plus solvent, that means total moles of, say, sugar plus water. That gives mole fraction. And last one is molarity, moles of solute, liter of solution. This is the volume. So you need to know all these definitions because this molarity is extremely important for all these different property calculations, the temperature, freezing point depression, boiling point elevation, because those are defined by molality. Now if I said that I'm increasing temperature, would you expect any change in this case, molality value? Would number of moles change if I increase temperature, or kilogram of solvent change? Answer is no, because mass has no effect on temperature. So this also has mass, this is the mass, it's not going to change. This is moles, this is moles. Is number going to change as you increase temperature? No. So top number is moles, it's not going to change. What about the volume? Is it going to change as we increase temperature? Yes. If I increase temperature, volume is going to go up. So liter is going to increase, and that means molarity is going to change. So among all these properties, it's only the molarity that's going to change because of the change in temperature. The other ones are independent of temperature. So keep that in mind. So that's all about definitions and temperature effect. Next type of question would be on one molarity calculation. Again, I'm going to remind you this calculation. I think it was problem type 3. Molality calculations. So we'd be looking for moles of solute divided by kilogram solvent. Now I picked this problem from the book, which is number 95B, chapter 13. Brown, Lemay, Burston book, 12th edition. So basically, the problem tells us that we have 0.10% of glucose in blood. So they're saying that we have that much glucose in blood, and from there we need to calculate molality of glucose. So that's what you need to calculate when percent of glucose is given. Now this is how you do it. 0.10% means out of 100 you have 0.10 glucose. So obviously the rest would be water. You mostly have in blood water. Water is the solvent. So gram of water in blood is given by 100 minus 0.10, and that's 99.10. That's gram. And then we change it to kilogram, because that's kilogram of solvent. We need to have kilogram of solvent. So 99.10 divided by 1,000, that makes it kilogram, because this is gram. So right now we got kilogram of solvent. But keep in mind why we subtracted 0.10, because this percent is out of 100 gram glucose plus water. That makes 100. So that's why we had to subtract the mass of the glucose to get mass of water, which is the solvent. Then from there we got the kilogram of solvent. Now we need to know the moles of solute. Now how do I get the moles of solute? I'll just give you the hint here. So solute is C6H12O6, which is glucose. The formula of glucose is C6H12O6. Now from here you can get moles like this. We already know gram of glucose, 0.10 gram C6H12O6 times molecular weight is 180 grams C6H12O6. In case you forgot, 6 carbon, by looking at periodic table you find the mass, 12 hydrogen, 1 times 12, so that's 12 plus 6 of oxygen, and that gives you 180 gram per mole C6H12O6. Now that would give you 5.56 times 10 to the negative 4 moles of C6H12O6. And now I can get the molality. Is given by 5.56 times 10 to the negative 4 moles C6H12O6 divided by kilogram of solvent. We already got the kilogram of solvent, 99.10 times 10 to the negative 3 kilogram H2O, which is solvent. And that gives the final answer of 5.61 times 10 to the negative 3. Small m stands for molality of glucose. And there'll be one calculation similar to this in exam. So make sure you understand what I covered here. My next type of problem would be effect of solutes on colligative properties. This is fourth type, effect of solute particles on one of the colligative properties, vapor pressure, depression of vapor pressure. Vapor pressure goes down when you add more solute. Freezing point also goes down, depression of freezing point. Boiling point goes up, elevation of boiling point. Osmotic pressure is shown by pi, that goes up. So these are the properties that depend upon particles. Why we are calling it particles? Because sometimes you may add one compound, but that breaks down into more than one particles, like sodium chloride in water. Each sodium chloride breaks down into sodium plus and Cl minus. with two ions. So let me first give you the background before I go over a problem. Now, why it's like this, why vapor pressure goes down when you're adding a non-volatile solute. It has to be non-volatile. Say I have a sample here, it's an enclosed sample, and I have pure water, for example, or any solvent. Now pure water can evaporate, and after some time there will be an equilibrium, there will be no more new vapor on the top, and that will be the vapor pressure at that particular temperature. Now this is the case with pure solvent. Each molecule can evaporate without any problem. So when I have pure solvent, after some time there will be an equilibrium. Equilibrium pressure would be vapor pressure. Pressure is equal to vapor pressure for that particular solvent. Now, let's assume that I added within the same sample a few non-volatile solutes. Let's make it darker and bigger. So these are sodium plus and Cl minus. Now, how is it going to affect the vapor pressure? Now think about this. This is not volatile, that means they cannot go to the vapor phase. But their presence is going to prevent some of these water molecules from going up or evaporating. So what happens is, these are just by staying around here is preventing some of these molecules from going up. So that means fewer molecules will be, water molecules will be going up, so vapor pressure will go down. And that's why when you add non-volatile solutes, vapor pressure would go down. Now the question is, why boiling point would go up? Boiling point is defined as the temperature at which vapor pressure equals to outside pressure. If I have, say, 1 atmospheric pressure here, because of outside air, if I have 1 atmospheric pressure, it's pushing every molecule down at that pressure. So you need to increase the temperature until the vapor pressure is equal to outside pressure, then we get the boiling point for that particular solvent. For a pure solvent, there is nothing to prevent these solvent molecules from going up. But when you have non-volatile solute, that's going to prevent some of these molecules in going up. So in order to have same pressure as 1 atmosphere, you have to increase the temperature so that there will be more vapor going up. So that means boiling temperature has to be increased because of the fact you added non-volatile particles in the solution. Now what about osmotic pressure? Osmotic pressure depends upon number of solutes. If I have more solute, there will be greater osmotic pressure, which is the pressure on it that is exerted on the semi-permeable membrane. So you have a pressure here, you have a solute particles here, then pure solvent goes from the other side. So that's osmotic pressure and osmosis. Solvent going from more dilute solution to more concentrated solution. Now, what about freezing point? Why there is a depression of freezing point? As you cool down a liquid, the particles will move much more slowly. That means they will try to cling together because of their internal forces. Now that's before you add something else. So if I added just a pure solvent, as I cool down, their motion is decreasing, so their internal attractive force is operating, bringing them closer, and then finally they freeze. But when I have some other particles, non-volatile particles sitting in between, they're separating them. They're not allowing them to come close together, or they don't feel attracted to each other that strongly because of this separation. So in order to give them that extra attractive force, you have to slow down these particles which are separated, so cool down farther, so that these particles would now cling together and finally will freeze. So freezing point is going to be depressed, or you have to get to lower temperature to get a new freezing point after you add non-volatile solid. So that gives you the understanding part. Now let's go over a specific example. Now this problem is coming from chapter 13, number 71. What they're doing in this problem is they have 0.120 molal, this is the molality, glucose they added. They have one sample with glucose. And how many particles we're getting? Glucose doesn't break up. It's not an ionic compound. So you're going to get 0.120 molal particles coming from glucose. It's the same as this number. They're also adding 0.0, this is the second sample, 50 molal lithium bromide. It's an ionic compound, so it breaks down into two particles. So it's going to be 0.050 times 2, because two particles are two ions. Lithium is one of them, Br is another one. So you need to multiply this by 2 to get the number of particles, 0.100 molal particles. And the third sample, 0.050 molal zinc nitrate. Okay? Zinc nitrate would break down into 3 ions, zinc, 2 plus, and 2 NO3 minus. So 3 particles. So what do I have here then? 0.050 times 3, 0.150 molal particles. Question is, in which case boiling point would be maximum? Remember, boiling point is going to be increased as you are adding more and more particles, non-volatile particles. We added maximum in this case, so boiling point would be increased significantly here, so that would be maximum for this. And boiling point next would be this, and least would be change would be here. So this is a qualitative type of question. I can ask you about boiling point depression. Maximum boiling point depression would be for this. Same would be the case with a vapor pressure. So make sure you can answer problems like this. So you look at how many particles are there. Now, type 5 problem. Again, this is, I'm picking another problem from the book. This is number 73C. Kf value is given, that freezing point depression constant, 1.86 degrees centigrade per molal. And question is, I'll give you all these numbers here. They are adding 1.50 gram of sodium chloride in 0.250 kilogram H2O, which is the solvent. So what is the freezing point of the solution? So that's what you need to calculate. The calculation is straightforward. You need to apply this. Delta T equals to a constant, Kf, times the molality. Now, first you calculate moles of ions, moles of particles from here. So it's basically 1.50 gram NaCl times molecular weight is 58.5 gram NaCl, giving 1 mole NaCl. We get this number from periodic table by adding 1 sodium and 1 Cl, and then 1 mole NaCl, 2 mole of particles, or 2 moles of ions, which is same as particles, and this is 0.0513 mole ions or particles. That's what you have in sodium chloride. Okay, now we can calculate now molality. M value would be given by 0.0513, that's the mole of ions coming from sodium chloride divided by the kilogram of solvent, 0.250 kilogram H2O. Because they gave you that 0.250 kilogram, and that gives you the value of 0.205. So now we have all these values to calculate. So delta TF, depression of freezing point, will be given by 1.86 degrees centigrade per molal times the molality value, 0.205 m, and that will give you 0.382 degrees centigrade. Now remember, whenever you add anything non-volatile, this is non-volatile, sodium chloride, freezing point is going to be depressed. Now it's depressed by this much. So what is the final freezing point? So freezing point is given by 0 minus, you subtract this value, it didn't go up, it went down. 0 is the pure water, pure H2O, that's 0 degrees centigrade. This is 0 degrees centigrade. That's the freezing point of pure water. Now you subtract this because it has gone down by that quantity, minus 0.382 degrees centigrade. It's the freezing point of the solution. Similarly, you can do boiling point calculation, where boiling point would be going up, and you have to add that number. Now the last problem would be one osmotic pressure problem. This is problem type 6. This is coming from chapter 13, and our example that I have picked is number 77 from Brown, Lemay, Burston book, 12th edition book. Question is, what is osmotic pressure in a solution? So we are going to get pi equals to what? Now this is the equation you're going to use. Osmotic pressure equals to molarity RT. So they gave you 44.2 milligram of aspirin. Aspirin is the formula, they gave you the formula CnH8O4. And then from here you calculate gram. 1000 divided by 1000, it gives you a gram of aspirin. And then from there you can calculate moles. I'm assuming that at this point you know how to calculate moles from the formula. So once you get the moles of this divided by volume, volume is 0.358 liter. So moles of the quantity you get here divided by liter, that gives molarity. So you get this number. Our value is already known, which is 0.0821 liter atmosphere Kelvin mole. And temperature has to be in Kelvin, and that is given 298 Kelvin, that's the room temperature. So make sure you use this number coming from here, and then that gives you osmotic pressure. So all these will be on the test. Make sure you read carefully, understand the concept, and do problems like these, and then you'll be well prepared for the very last exam.